Sales prediction has become a popular topic in machine learning and data science. Many companies want to exploit the power of machine learning models to anticipate their future sales, and Google is one of them. This is Google Store, and we are going to present our prediction of Google Store sales.
For an online store, customers who visit the store through internet will leave their footage and the store will record it and use it for future prediction. Conventionally, some online shopping websites use logistic regression or random forest to make prediction. However, they are not good enough for a large dataset or consumes a lot of time to build prediction model. We use two new models called light gradient boosting method and recurrent neural network with long short-term memory, which are thought to be more reliable and efficient on large-scale dataset. We will compare the performance of the two models.
This Google Store prediction comes from a Kaggle computation for which we need to predict the total revenue spent by customers within 3 months after the computation ends.
Our evaluation metric is root mean squared error, which is calculated by the square root of the sum of squared yi minus y hat divided by the number of customers, where yi is the natural log of actual revenue and y hat is the natural log of the predicted revenue for a customer.
Our training dataset has 25 GB and test dataset has 7 GB. The flattened dataset after parsing has around 100 features and 1.7 million samples. Most of the features are treated as categorical features and the rest of them treated as numeric. For categorical features, we use one-hot encoding to convert them into numeric representation. During data exploration, we obtain insights by making some plots. The plots above and below show revenue versus time and the number of visits versus time, respectively. These random patterns shows that revenue has very weak correlation with time and visits. For the next sum plots, we break customers into two groups. One group made purchases in Google Store and the other one did not. Each group is plotted versus different categorical features to have visual understanding of their predictive power. For missing values, we impute categorical features by adding a new level called NA and numerical features by the average of that feature. If 80% of a feature is missing, we drop that feature because we think it contains only little information. One problem of one-hot encoding is the dimensionality explosion, so we need principal component analysis to make feature selection. The goal of PCA is to reduce the dimensionality of data while retaining as much variance or as much information as possible. Before PCA, we first normalized our cleaned dataset. To determine what number of dimensions to be left, we searched through 49 possible values using cross-validation and light gradient boosting model. The best number of components turns out to be 290. After we obtain the reduced dataset, it comes to the models. Light GBM is a gradient boosting framework using tree-based learning algorithm, but it differs from other tree-based algorithms. Because Light GBM grows tree vertically while other algorithms grow tree horizontally, it will choose the leaf with max delta loss to grow. That is, leaf-wise algorithm can reduce more loss than a level-wise algorithm. Another good part of Light GBM is its high speed on large-scale dataset, and it takes lower memory to run.
Most people are familiar with recurrent neural network, whose standard version has only one single layer. As for long short-term memory, it also has this chain-like structure, but it contains 4 interacting layers, which always performs better. That's why we choose long short-term memory in our project.
We used grid search to find the best combination of parameters. The plots show both the training and validation of root mean square error after each trial. For light gradient boosting model, after the 5th trial, the discrepancy of root mean square error between training and validation keeps increasing, which means that our model starts to overfit, and we should stop at the trial 6. The best root mean square error found by LGBM is 0.61. For LSTM, the first 3 models are underfitting because the number of epochs are set to be low. After we increase the number of epochs, the performance tends to be stable, and the best root mean square error found by LSTM is 0.389.
So, what's the meaning of revenue prediction? If you're a businessman, it costs you $20 to purchase each book, and now you want to make money and sell them for $60 each. No one will buy it, of course. However, according to our revenue prediction, Alice is willing to pay $40, so we offer her $20 coupon. Whereas Bob is willing to pay $35, so we offer him $25 coupon. They will be happy to buy your books and you can make money.
Thank you.